say that the inversion changes the orientation of space-time.
Yes.
I'm not sure to understand what is the orientation of space-time.
So the orientation of space-time is defined by the volume form of space-time. So there are several ways of saying it. So one is the orientation of space-time is the handedness of the space-time is parameterized by the Levitivita tensor. Okay, that's something you're more or less familiar with. Another way of saying it is that the volume of space-time is, yeah. So let's say it in terms of the Levitivita tensor. So you have okay, and this is a choice of orientation. So these guys are totally antisymmetric, right? And you choose an orientation, so this is 1, okay? This is choosing some handedness of your axis, okay? Now, this epsilon tensor transforms under a conformal transformation. And what I'm saying is that the epsilon tensor, the sign of the epsilon tensor in the x tilde frame is minus the sign of. I mean, a simpler transformation that changes orientation is parity, right? Because you reverse, so just in standard Poincare transformations, you invert 3 special coordinates. So when you do the transformation, in that case, it's very simple, right? You get 3 minus sign, so you get that epsilon maps into minus epsilon. So you change the orientation.
But PT would not change space-time.
PT will not change the orientation of space-time, yes, because you have an even number of minus signs.
The orientation,
yes, yes. You can try to show that, yes. It's true in any dimension. Yes.
I'm wondering a little bit about the last part of last lecture.
Okay.
First thing, how do you show that if you take the stress energy tensor with a scaling vector, you get current of that symmetry?
Well, so to show that for an arbitrary theory, you have to work hard. I didn't really show it from first principles, even though I did show it for a particular example of lambda phi to the 4, right? I started with the, well, at least I sketched how you would do it. So I'm trying to think what I can tell you. So you were not happy with the statement that there is a choice of a stress tensor for which this is the conserved current associated to the corresponding space-time transformation. So did we agree that this was true for translations and Lorentz transformations?
But how do you see that it is the current associated to, say, rotations that...
Yes, so for that, for this particular case, it's really straightforward. All that you do is just apply standard Neller's theorem. And I mean, in the formula for the current associated to a transformation, you have the variation of the field with respect to the transformation. And just really compute associated. So actually, I should say that in the homework that you're going to get, since maybe this discussion of stress tensor was a bit unfamiliar or maybe a bit fast, you'll work out several examples of how to compute the stress tensor in different theories. So I'll just sketch it how to do it now, but you will have, I think you'll do it for scalar fields, for Maxwell. So, but if after that you still have problems, we can go in more detail. But associated to rotations. So what's Nether's theorem? So let's imagine we do it for a scalar field. We had this, and then we had the variation with respect to the field minus I guess k mu, which is the total derivative. Remember that this was the term that if you make a transformation, the Lagrangian can change up to a total derivative. Right? So now the thing that I just asked you to verify is that maybe the point is that it's not so clear what delta phi is under a Lorentz transformation. So what is delta phi in the Lorentz transformation? Yes. Another way of writing it, which is more convenient, is that's why I write it this way. Is because essentially a Lorentz transformation, and actually this is something that I'll describe later, how fields and operators transform under Poincare and conformal transformations. But essentially what you say is that a scalar would transform under Lorentz transformations well, there are several ways of writing this, but okay, like this, right? So it rotates the orbital part of the field, the space-time coordinate, but since it's a scalar, it doesn't act on the spin part of the field because it's a scalar. So now let's look infinitesimally what this is. This is phi of x plus, I just have to do, this omega is small by definition, I'm doing an infinitesimal transformation. So this gives me omega mu nu x nu d mu phi of x. I keep changing what I mean by phi. But so now what is delta phi? Delta phi of x is the variation in the rotated frame minus the variation, minus the field at the original frame. So this is just omega mu nu x nu d mu phi. Okay. So now all that you have to, you have an expression of t mu nu that you extracted from the translational invariant. And now, just plugging in explicitly that this is delta phi for arbitrary rotation, you see that you'll be able to write this exactly in this form, where v nu. So it just follows from a straightforward calculation. To show this for a scale and conformal transformation is a bit more subtle because, as we saw in the example of lambda phi to the fourth, if you take the canonical stress tensor and you write it in the current in terms of the canonical stress tensor, it doesn't quite take this form because you have this extra term that you improve away so that you can write it this form. But I showed explicitly that there was a way of going from the canonical stress tensor to this nicer stress tensor by adding something like, what was it? Something like which was conserved. It conserved. It was transverse, conserved. It generated the same momentum and energy and the same Lorentz transformations, but it had the property that, with respect to this new stress tensor, the current could be written this way. But you have to have some insight. It doesn't always naturally come this way. You may have to improve it to write it this way. But if you want, you can just write the canonical one. You'll get something that will not be exactly like this. In general, this will have an extra term. And then with some insight, and I think you have an exercise to practice this, you can define an improvement terms in such a way that then you can write in terms of a new stress tensor. But the intuition I was trying to give, why this should be true, is the stress tensor knows about deformations of space-time. So any space-time transformation is parameterized with the stress tensor. And what type of transformation you made is controlled by the infinitesimal vector field. More questions? Yes. Well, so the CPT invariance is not something that you put by hand, it's something that you prove. Actually, it's a deep theorem of quantum field theory that if you demand that the theory is connected to the identity, it's automatically CPT invariant. So it's definitely a very non-trivial prediction of quantum field theory. So it's not something that you're demanding, it's just consistency of quantum mechanics, relativity, so unitarity and relativity forces this on you. So now if there's an experiment that measures that CPT is broken, this would be completely dramatic. It would tell you that at some level, CPT, quantum field theory has to be replaced by something else. But there is no constraint whatsoever on whether C, P, or T are conserved. And as I said, in important theories like the standard model, they're broken. But importantly, not CPT. Yes?
Is there a physical signification to that term that we had? Because it looks like a boson propagator.
Well, the way this seems completely ad hoc now, but the way you can derive it is, remember that I said that the stress tensor can be obtained by coupling the theory to gravity. And this term arises because there's an ambiguity on how you couple your theory to gravity in such a way that you get the flat space theory. And this is the term that arose by varying respect, and actually this is something I think you have in the homework. We'll give you this if the action has this term. So it's a conformal mass. Actually, so in some sense, this guy is called a conformal mass. So if you have a scalar field coupled to gravity, it can acquire a mass just by coupling to curvature, even though it has no mass term in flat space. And this guy is called conformal mass. More questions? I would take advantage if it was you. No? Okay. Good. Okay, so yesterday I reminded you of how symmetries in quantum in field theory are encoded in terms of conserved currents, and how we can construct conserved charges out of conserved currents. And I motivated this general construction of the current associated to a space-time transformation from the stress tensor and the choice of a space-time transformation. And now, once we have a set of symmetries, so this gives us conserved currents. Associated to symmetries. And now, one of the things that we will do, I don't know if today or tomorrow, depends on how we go, is to use precisely the symmetries to constrain as much as possible the dynamics of the theory. So just like, to tell you a trivial example, if you have a theory that's translational invariant, and imagine you want to compute the correlation function between the magnetization at two different points in a magnet, mx and y. So if you didn't know any better, this would be an arbitrary function of x and y, right? But now what you can use is the fact that if the theory is translational invariant, this correlation function should be invariant under translations, and obtain, for example, that the correlation function is not an arbitrary function of x and y, but it's a function of the difference. The only thing that matters is the relative position of the two vectors. And in order to derive, well, there are several ways of deriving such constraints that symmetries impose on your correlation functions. And the next thing that we want to do is precisely see what are the constraints on correlation functions that conformal symmetry imposes. Okay. And now that we have the explicit currents, we'll be able to generalize this kind of simple consequence of translational invariance to an arbitrary conformal transformation. And we will see that this will give a very strong restriction on the form of the correlation functions. Okay. And once we fix the form of the correlation functions, some of them will be complete. The spatial dependence will be completely fixed. Then we will be able to extract. So remember that I said that in particular, conformal field theories, say in 2 dimensions, describe the critical behavior of thermodynamic quantities near the Curie temperature. And by reading off the correlation functions that will have these very important constraints due to conformal symmetry, we'll be able to read out the critical exponents associated to the behavior of these thermodynamic quantities as they approach the critical point. But before getting there, we have to first of all, understand how conformal symmetry acts on operators, like magnetization and so on. And then, so first, how they act on the operators that you want to compute correlation functions of. And the second thing that we want to do is how conformal symmetry constrains the correlation functions of those operators. Okay. But before doing that, just very quickly, let me tell you that, because I think it's important to remember, that this, in particular, scale transformations are typically, well, typically is not the right word, but like in a vanilla theory, like lambda phi to the 4 in 4 dimensions, quantum mechanically. Due to the thing I've told you already many times, that in field theory, generically, coupling constants acquire an energy dependence, and therefore you break conformal invariance unless this coupling flows to a non-trivial fixed point in the infrared, which is what happened in this example I told you about the Wilson-Fisher fixed point. So what I want to just now briefly mention is how this story of current conservation changes if the theory is broken quantum mechanically, and the symmetry is broken quantum mechanically. So we had that classically. There was a dilatation current associated to scale transformations, right? This follows that general rule that I contract the stress tensor with the vector associated to scale transformations, which is just x. And this current was conserved, which is just a statement that in this particular frame, the stress tensor is traceless. So now what we want to ask is, how does this equation, the conservation equation, get modified quantum mechanically. So can you make a guess what the right-hand side? So clearly now, the current will no longer be conserved because I've introduced a scale into the problem. So based on all the things I've been telling you in the last few days, I mean, could you guess what kind of right-hand side would capture the breaking of? Sorry? Delta function of? No, I mean, that's not the direction I was thinking. No. Yes?
It should be somewhere related to the beta function.
Exactly, yes. Because the fact that the theory has acquired a non-trivial energy dependence is precisely captured by the running coupling constant, which is the beta function, which is measured by the beta function of the theory. Okay? So now I'm going to motivate heuristically what the right-hand side has to be, just by doing some simple logic. So maybe that I said when we were discussing Nether's theorem, that if you make a transformation, like a scale transformation, and the object and the transformation is a symmetry of your theory, that this guy either vanishes or is a total derivative. Okay? That was the statement, it was a symmetry. Now imagine I do a dilatation in a theory that's in the quantum theory. So if I make a dilatation, just from the statement that imagine I have some coupling constant G, that has this beta function behavior. If I make a dilatation, which is a small change in the energy, what happens under that transformation is the coupling constant shifts. Precisely, right? Because now it has an energy dependence, so if I make a small infinitesimal change of energy, it will transform. Okay. So that means that the Lagrangian will change in precisely this form under such a transformation. So this is what will happen to the Lagrangian in a theory that was originally scale invariant if I make a scale transformation. Now I will not get zero anymore. I'll get something that measures precisely the breaking of the scale transformation, which is induced due to the beta function, is measured by the fact that now the coupling constant transforms as a scale transformation, which before it didn't, because it was classically scale invariant. And then there is a slight modification of the Nether theorem. You can still write down Nether theorems for any transformation that is not even a symmetry, that has the properties. Imagine you have a transformation such that delta L is some delta, some function. You can always construct by the same procedure that we did for the Nether's current an equation of this type. A mu J mu equals delta X. Okay? Of course, now this current is not conserved, and, but you still get an operator equation. It tells you that the divergence of some current is the variation of the action under some field transformation that is not a symmetry in general. So therefore, then we can put these two things together to conclude that quantum mechanically, the divergence of the dilatation current is precisely given by this delta, but delta we just computed. It's just this thing here. So it's the beta function of the theory, the variation of the Lagrangian with respect to the coupling. That's that. Okay? And this fits exactly with the expectation that you would have, that in a quantum field theory, the measure, the signature that scaling varia has been broken is that the theory has a non-trivial beta function. And this kind of behavior, quantum mechanically, is kind of perhaps the simplest example of a very important phenomenon in field theory, which is called anomalies. And in this particular one, it's called the trace anomaly. Well, it's called the trace anomaly for obvious reasons, because d mu t mu is just the expectation value of t mu mu. Okay. So the trace of the stress tensor is no longer 0. It has a non-trivial right-hand side. Okay. So actually, this way of thinking about it is even useful. Yes? It just means that this is a quantum mechanical. So I compute this inside the path integral. Yes?
So is this in some way related to Dyson-Schwinger equations, or is this just...
Schwinger-Dyson equation is something much more general than that.
Yeah.
That's just the statement that you can use the equations of motion inside the correlation function.
No, but it's just that the fact that you're doing it in the...
Well, there's just signals that I'm not just solving equations, classical equations of motion. That I'm evaluating this inside the path integral. So some vacuum expectation value of this operator. So let's consider it. So imagine you have a theory, and this will be a kind of a simple trick to compute. So if I have a theory which is a free, even a free theory, okay. Okay, let's forget about that. No, let's see if maybe this helps. So by now you should tell me that that you know that this theory is not conformal invariant. But now you can compute precisely by using this kind of trick. What is the trace of the stress tensor? Because we know that the point is that even classically, the operator m squared phi squared, which is the mass term for the scalar field, has a non-zero beta function. What is the beta function? Classically, of m squared. Can someone tell me? Sorry?
I just do something naive. I just differentiate this with respect to n, so I get n.
No, it's not that. The beta function, remember, that measures the dimension of the dimension of the coupling. So what's the dimension of m squared?
2. 2.
2. So that's why here you get minus 2 m squared. But remember that when the beta function is negative, the coupling grows into infrared. And that's what Rayleigh operators do, and that's why you get this minus sign here. Okay. So then by just applying this logic, what you find here, up to sines and factors of 2 that I'm not sure to be careful. Yeah, let me try to be careful. You'll get minus 2m squared times the derivative of the Lagrange with respect to m squared, which is just 1/2 phi squared. So you get minus m squared phi squared. So, and this is something that if you just write down the stress tensor of a massive free scalar field and do it kind of brute force, you will get exactly this. Okay? Yes?
Right.
Well, okay, so to be precise, this is an operator equation that is true inside any correlation function. So if you want, you can just think of it as an operator equation that you can insert inside any correlation function. So if I put here operators on, instead of just looking at the correlator of the stress tensor, I look at the correlator of the stress tensor with an arbitrary number of operators, I can just plug in this equation inside the correlation function. So maybe it's better to think about it this way. And now maybe...
But is that only true when you insert it into...
Yes, it's true when you insert the correlation function. But the point is that this can be included with an arbitrary number of other operators on the right and the left. Okay. So by using this example, you can compute, for example, what T mu mu for QED is at one loop. Maybe I mean it's a trivial exercise. I'll leave you to do it. Essentially, all that you have to do is vary the QED Lagrangian with respect to the coupling. Okay. Good. So now, in general, but this I may come back to this when we study two-dimensional CFT. Something very briefly that I want to mention.
Could you repeat what T mu is for QED at one loop as an example?
Okay, let's do it. Yes, let's do it. So let's look at this master formula. Okay. It's convenient to the Lagrangian of QED to write it like this. That's electric charge, right? Yes? So now what I have to do is just plug in the one loop running of QED, which I believe you've seen, the one loop at the function of QED. It's positive. The specific number is not very important. It's just E cubed over 12 pi squared. And now all I have to do is vary the Lagrangian with respect to E. So if I know how to do this, so it's going to be 1/2 E cubed F mu squared. Okay. So putting things together. It tells you that the trace of the stress tensor at one loop is proportional to F squared. Yes?
And so, question, wouldn't it be then easier never to calculate the beta function using renormalization, but just finding the T mu nu and then taking its trace?
Well, but computing this as one loop for a complicated theory like QCD is not easier than computing the beta function directly. But I mean, it's completely equivalent, yes. Okay, so that's kind of one of the simplest examples of the phenomena of anomalies in field theory, where a classical symmetry, which has a classical conservation law, is violated quantum mechanically, but violated in a very specific way that's still useful. So very briefly I'll mention, and again, I hope to come back to this when we study in two dimensions, is that there is another way in which a theory that was classically conformal invariant can cease to be conformal invariant. So what can happen is that I'll just briefly mention it because I think it's important. So if you can start with a theory that's conformal invariant, a conformal field theory in flat space. For which we know that T mu mu is 0. Now, what can happen is the following. So in that case, the non-zero right-hand side of T mu mu arose due to quantum effects, because I had a non-trivial quantum mechanical beta function. Here, what can happen is that a phenomenon that happens is that I now couple conformal field theory to a curved background. Okay. Now, what can happen is, depending on the geometrical properties of the curved background, what can happen is that T mu mu, the expectation value of the stress tensor in the curved background is no longer 0. So it's broken. This guy is known as a conformal anomaly. But the breaking, the kind of breaking that can appear on the right-hand side is of a very specific form. It's not an arbitrary breaking. It depends on very specific details of the geometry that you couple your theory to. So let me just write down a formula without deriving it, because actually deriving this is quite complicated. But let me just tell you, just to give you a flavor of what this thing is. So you get something on the right-hand side. And then I'll tell you briefly why I'm telling you these things. Again, because these numbers will be important. So the first thing to say is that whatever appears on the right-hand side will have to have dimension 4, okay? And these are essentially the two independent geometric covariant objects that you can construct out of the metric. They have dimension 4. ThisWijkl square, thisWijkl is the wild tensor associated to the metric, and it's essentially Riemann squared. It's a funny combination of Riemann, Ricci, and scalar curvature. And then you have what's called the Euler density. So, okay, let me say this is wild. This is Euler. And this is just a different looking combination of Riemann, Ricci, and scalar. Okay. Now, it could happen, of course, that if I plug this back to flat space, the right-hand side vanishes, because the wild tensor, well, all the curvature invariants in flat space vanish. But if I'm on a suitable manifold, the right-hand side will be non-zero. But the breaking of the conformal symmetry is just parameterized by two numbers. By A and C, which are numbers which is encode part of the DNA of the theory that you have. So these numbers are theory dependent, and I'll call the conformal anomalies. And these are things that can be computed, say, in perturbation theory. And the reason I'm mentioning this is the following, is that, and actually this is something that I will prove in 2 dimensions where things are a bit simpler. If you do it in 2 dimensions, so this was in 4 dimensions, okay, I didn't mention this, but of course this was in 4 dimensions. If we do it in 2 dimensions, things are a bit simpler. You get minus C over 12 times R. R is the scalar curvature of the background. And in this case, you only have a conformal anomaly. And what's special about this C that is not manifest from this discussion, but that we will prove, is that C, this number, is a function that measures the effective number of degrees of freedom of a quantum field theory. Okay? It has the important property that if you compute the variation of C as a function, so imagine you have a renormalization group flow from some one theory to some other one. The statement is that this function is monotonically decreasing. And a very precise sense that we will make precise when we study 2 dimensions measures the effective number of degrees of freedom of the theory. Okay. In 4 dimensions, in 2 dimensions, it has been proven that this C has this monotonic property, which is very non-trivial. which fits the intuition that you have when you do a renormalization group transformation from the ultraviolet to the infrared. You are neglecting high energy degrees of freedom, right? You're forgetting about the very high energy modes and just focusing on the long distance modes. And therefore, you expect that the number of degrees of freedom is decreasing because you are eliminating the very high energy mode. And this Zamolodchikov C theorem makes this non-precise. Now, it has been conjectured in 4 dimensions that a similar role to C in 2 dimensions is played by this Euler anomaly A. And actually, last month, there was just a paper claiming to have proven the analog statement in 2 dimensions, namely that this conformal anomaly A in a 4-dimensional quantum field theory is an strictly monotonically decreasing function of the normalization group, which is, if true, I mean, people are still, I think it's true, actually. But this would be, well, this, by the way, was originally conjectured by Cardi that this would be true, but now there seems to be an explicit proof. And the last thing I want to say about this is that even though these numbers seem to only appear when you're in curved space, because again, I said that the right-hand side of this vanishes, right, if you're in flat space. It turns out that these numbers A and C, you can also, they also appear in the flat space theory. But they don't appear in the 1-point function. They appear in the higher point functions of the stress tensor in flat space. And one very simple, and we will see that when we do 2 dimensions more concretely, but one very simple way to motivate that is that if you take the derivative with respect to the metric of this equation and then set it to flat space, the variation of this will bring down 1 factor of the stress tensor. So you get the correlator of 2 stress tensors. And then you'll have to vary this with respect to the metric and set it to flat space. And therefore, you get a non-zero result. So you can extract these fancy numbers that appear when you couple the 3 to curve space just by studying 2 and 3-point functions of stress tensor in curve space. I'm sorry, in flat space. Okay?
But one question then this C, even though if we have a conformal field theory that is not conformal anomalous, is still there, right?
Is it still sorry?
The C will still be there, even though if our theory is not conformally anomalous.
No.
If the theory is conformally invariant, we will also have the C there.
Yes, yes.
So
I'm saying that a conformal field theory, generically, even if it's exactly conformal in flat space, will have a non-trivial C and A that you can capture by studying correlators.
But why do we call it then conformal anomaly? If it's
well, because if I had coupled that theory to curve space, the trace would be non-zero. Yes?
If we have a theory in flat space, then there are many ways that we can couple it to curved space theory. So to make it a theory in curved space. So are these numbers A and C going to be independent of the way
yes,
we couple
yes, and that's something that's not trivial to show, yes. I mean, they're really invariant numbers of the theory. So it doesn't depend on the theta. Okay, so now that I told you this little thing, the next thing that I want to do, our ultimate goal, again, just so that we don't lose focus, is that we want to study the constraints that conformal symmetry puts on correlation functions of operators in conformal field theory. So the first thing that we have to now understand is how conformal symmetry is realized, how conformal symmetry acts on operators in a conformal field theory. Because in order to determine how the correlation functions of the operators in a conformal field theory are constrained by symmetry, we need to understand how these operators transform in the conformal symmetry. Okay? So now I want to discuss okay. So again, what we want to know is how operators OX I call it operators or fields. More generally, it's an operator because this operator could be a composite operator constructed of the microscopic fields depending on the Lagrangian. So, for example, if you are doing electromagnetism, an example of O could be et mu nu. And what we want to know is how these guys transform under a conformal transformation. Okay. Just like I did when I discussed space-time symmetries, it will be useful to first think about a subgroup of transformations of the conformal group, which are the Poincare transformations, and first remind you how operators in field theory transform under Poincare transformations. Okay? So let's start first with So let me remember what these things were. It was just transformations of this type. That involved a translation and a Lorentz transformation. And now what we want to know, something that you already know, which is if I have a field phi, or an operator phi, v of x, I have to tell you two things about this operator. I have to tell you, so there is some geometrical data, or geometrical transformation, which I call the orbital transformation. That tells you how the spacetime transformation acts on the argument of the field, on the position of the field. This is kind of universal. It acts the same on all fields, essentially. Just a transformation is the geometrical transformation on the argument of the fields. And then there is a internal or spin transformation that depends on our choice of operator, phi a. Okay. And essentially depends, so this label A essentially is a label that tells you the representation of the Lorentz group, not of the Poincare group, of the Lorentz group. Under which the field transforms. Okay. So actually, if I look at an operator in a relativistic field theory, all I have to tell you, even though it has Poincare symmetry, all I have to tell you about the operator is its transformation under Lorentz transformations. The translation transformations just act geometrically. They shift the argument of the field. Okay. So now let's review something that you know. So if I make this Poincare transformation, how does the field transform? So if I make a Lorentz transformation, what you have to do is identify the rotated field at the rotated point with the original field at the original point, by taking into account that if the field is non-trivial, transforms non-trivially under Lorentz transformations, that you have to make a non-trivial transformation in the internal indices, in the spin part of the field. Okay? So hopefully this is something that you've seen before, how fields transform under a Poincare transformation. Another way of writing it that is useful is just doing a trivial relabeling of the points in the field. So x tilde is gx, but I will like, for some reason, I don't know why, but I like it to put it this other way. All I'm doing here is replacing x, these are relabeling of g inverse x, so I have this. Okay. Good. So let me tell you a couple of things, a couple of properties of these transformations and the Lorentz transformations. As I said before, there are two types of ingredients that go into the transformation of the field. One that acts on space-time only, this part. You shift the value, the argument of the field by the choice of transformation you made. And then there is a spin part of the transformation that acts on the internal degrees of freedom of the field. And that's the origin of this rotation matrix here. Let me point out something that you can see from this formula, is that the transformation, that if you write the transformation in this way, the transformation on the spin part of the field is opposite to the transformation in the space-time part of the field. So here I have a G inverse, well, here I have a G. And that is required for consistency of Lorentz transformation, Poincare transformation. Okay. So how would one check that this is a consistent? So when we say that the Poincare group or acts on fields like this, what we really mean is that we can represent, so the Poincare group, essentially what it means is that we're representing the Poincare group on the field. Okay? So this means that if I make two consecutive transformations.
Question?
Yes.
The argument of phi b
Yes.
is supposed to be gx?
No. Gx is here. So what I do is...
So now if we look at phi a transform to LAB phi b, so why the argument doesn't transform?
You mean here?
Yeah.
No, because think what we're doing. Okay, I'll try to draw a picture. Well, first of all, if you did that, you would convince yourself that that wouldn't realize the Lorentz symmetry on the field. If you did two consecutive transformations, the transformation on the field you would get would not be a Lorentz transformation. But intuitively, and that's something that you have to sit down and convince yourself, is that you start with a field phi here at the point x, and you make some transformation to x tilde. The thing that makes sense is to compare the value of the field at the new transform point with the value of the field at the original point. And that's what I'm doing. Now, if it's not a scalar, you have to worry about the fact that as you do this transformation, the indices also transform, this LAB. But the way to really prove it, and maybe I'll leave it as an exercise, to see that. So one question would be, what properties should these matrices LAB satisfy? So there's a consistency condition. That says that if I make the transformation, I can make a transformation now, which is the product of two Lorentz transformations, of Poincare transformations. I can do a transformation which is G1 followed by G2. Okay. So I can analyze how the field transforms under such a transformation in two different ways. One, I can just use that rule.
When you say G1, G2, do you mean first G2 and then G1?
No, first G1 and then G2. Okay, and now maybe I'll leave this as a little exercise, and if you don't succeed, I'll do it in the Blackboard on Monday. But what I want you to show is that now if you make the transformation by first doing a transformation, transforming with G1 and then with G2, that equating the fact that 1 has to equal 2, because I made the same transformation. I just did it in one case in one shot, and in the other case in two little steps. What you should find is that LAC G1, LCB G2 is LAB G1 and G2. Okay. And this just means that, so what does this mean from the mathematical point of view? Yes?
The L is a representation of the group.
Yes, very good. So it means that this matrix LAB of G is a representation of the Lorentz group. Okay, good. So can one, let's see, I just want to get some feedback. So is it clear, do you have some intuition of why I do not have to associate internal quantum number to the Poincare, to the translation part of the Poincare group?
I can make a guess. I don't know if it's right, because so if it's abelian, then the representation is always going to be one-dimensional, the irreducible ones. So we can absorb this vector. It's going to be a phase vector. We can absorb it in the transformation of the external of the momentum of the fluid. It's not that.
Okay. I was looking for a much more physical answer. I mean, maybe there is some truth in that. I have to think more about it. But the point is this: that so this is your space, okay? And what's special about translations is that you can go from any point in space-time to any point in space-time by applying a translation. Okay? So if you know how the field transforms at the origin, just by acting, conjugating with translations, you know how the field will transform. This was at the origin, right? At any other point in space-time. Okay. And if you look at how, how the Poincare group acts, say, at the origin, which subgroup of the Poincare group leaves the origin invariant? The Lorentz transformations, right? So all that I have to do is specify the transformation properties of phi under the transformations that leave the origin invariant, which is the Lorentz transformation. Once I tell you what the transformation at the origin is, just by using the symmetry, you know how it transforms everywhere else. Okay? And that's why fields just carry this label under Lorentz transformation, because that's sufficient to know how it would transform anywhere. Yes?
I think it is worth repeating if you don't mind.
Okay. Is something specific you want me to tell?
I think it is worth just repeating
Okay.
because of the beginning. I mean, why we know that, why we can go from phi at 0 to phi
Okay,
at x.
so remember from quantum mechanics? That if you know an operator at phi of x, okay, good, yeah, so maybe you should have. If you know your field at the origin, how do you relate phi of x with phi of 0? In quantum mechanics, or in classical mechanics? Sorry? Yes, but so how do I do it?
With two exponential with a to the EPX.
Yeah, so let's do it first for time. So you have e to the ht, right? E to the minus iht. I mean, this is the Heisenberg equation of motion that tells you how an operator at the origin gets transformed to an operator at finite time be a wave. That's true also for translations, of course. So this is precisely the statement that if you know the behavior of phi 0, that you can translate the value of the field at the origin to any other point in space-time by conjugating by translation. So if you know, okay, maybe I can put, should I give more details? Maybe.
Not sure.
Okay, unless there's some specific. So, but that's all I was meaning. So that if you know the value and in the transformations of the fields at the origin, you know it everywhere else, because you can get to any other point just by conjugating with the translation generators. Yes?
The matrix equation for the representation of the microarray group.
Well, that's a Lorentz group, yes.
The Lorentz group. I think you have to act with G1 or G2 on phi.
I act first with G1 and then with G2.
So G1 has to be on the right.
Sorry?
So G1 has to be on the right.
No, because, no. Okay, let me do it. Should I do it? No, think about it. So first you act with G1. So you have LABC, phi C. Now act with G2. G2 will act on phi C. So it will be LG2, C, B, phi G1, G2.
But when you have LAC G1, LCB G2, this acts on right. This looks like the first reactor change to and then so on.
Okay, so let me try to do it. Should I do it? Or why don't you try to do it? And I can do it now, or I can do it on Monday. I think it's better that you try a little bit. I mean, this is something that you've probably seen before. But no, I mean, remember that when you have the spin part of the transformation, when you act on G2, okay, so maybe I should just sketch quickly how it goes. At least the spin part. So if I act first with G1, I'll get L, A, C, phi C. And now if I act with G2, okay, so I have to put the argument, of course. And now if I act with G2, I act on this index, right? So I have LAC G1, LCB G2, phi B. Okay, good. Okay, so now let's look at an infinitesimal transformation. Sorry, let me.
Jaume?
Yes.
Are we assuming that the spin part of the field is invariant under translation term?
invariant. I mean, it just doesn't act on the internal degrees of freedom. It only acts on the coordinate.
Okay. Sorry.
Yes.
It's like
So I wanted to show you something, and now. Okay, let me just work it out.
So a question.
Yes.
So do the L's commute? I mean, so if you have LAC G1, LCD G2.
Sorry?
I think so. Or maybe. No. Okay.
So now let's look at the infinitesimal transformation. So let's look at infinitesimal transformation. So we have that how do I want to write it? So what I want to say is that x goes to x tilde with gx, which for an infinitesimal transformation will be x, okay, mu plus b mu, okay, where b mu is an arbitrary Poincare transformation. So now let's plug that into that equation and use the fact that this LAB is a representation of the Lorentz group. So you can write it, okay, sorry. I mean, N mu here, right? I mean, you have the vector associated to translation is a constant. So here I have A mu P mu plus 1/2 omega mu. Okay, no, here is the Lorentz, sorry. So this is just Lorentz, right? So I have I over 2 omega mu nu m mu nu. And this is some matrix. M nu is a representation matrix. Of the Lorentz. Lorentz. So for example, for a scalar, this would be what?
That's
Sorry?
that's mu T mu minus that's
No, I'm talking now only about the spin part of the transformation. So for a scalar, this would be 0, right?
Yeah.
The representation matrix is 0. So okay, so maybe just to write down some formulas for this m mu nu AB for a scalar field is 0, right? That's what it means it's a scalar. For a spinor, so can someone tell me for a spinor what these matrices are?
Sigma mu nu
Sigma mu nu. Okay, what is sigma mu nu?
is the commutator. The I over 2 or 4 of the commutator of the two sigma.
Of the two?
Yeah.
2 gamma.
Yes.
Okay, so the coefficient has to be fixed, but that's easy. And then, just to give you one more example, we have a vector. So what would it be for a vector? Okay, that I don't know what hard.
Something like an identity?
Sorry?
Something like an identity.
No, the identity. Well,
I mean, a vector.
one, I mean, if someone can write it down, it would be great. I feel very lonely there. Sounds good? Sounds good. So actually, so in order to check that this is true, what would you have to do?
to put it in the see if it satisfies the commutation relation.
Yes. So what you would have to check is that as matrices, M mu M rho sigma, say A, B, satisfies that crazy commutator eta mu rho M mu sigma plus these other terms A, B. That's what it means to be a representation of the Lorentz algebra. Okay. And if it's not difficult to construct explicitly what you had a tensor, you would know how to do it. The point is that for Lorentz transformations, all representations can be constructed from the knowledge of two basic representations, which is the vector and the spinor. If you know how the vector and the spinor transforms, you can construct any representation by taking tensor product of those. Just like when you study SG2 in quantum mechanics, if you know how you can construct all representations of SG2 starting from the spin 1/2 representation. So for Lorentz, it's exactly the same. Okay, so maybe I'll just finish by writing the infinitesimal form. The next lecture we'll start with how to generalize this story where we have the action of conformal transformations on operators. And we will see that apart from having to specify the Lorentz properties of the operator, we will have to specify the quantum number under one more operator, which is the dilatation operator. And that's where the dimensions and critical exponents will come from. Okay, so now that we have this, let's look at the infinitesimal transformation. So we're going to have, so I'm looking at this, at the box formula and this, and expanding to leading order. So have phi tilde A of x equals, well, the identity, so delta AB, plus 1/2 omega mu M mu AB. That's what I was calling the orbital part. And now I have to multiply this by phi B evaluated at x minus, because, okay, something I should say is that, of course, if I make an infinitesimal transformation like this, G inverse of x, and so if this is G of x, what is the infinitesimal form of G inverse x?
X minus.
X minus, yes. And the thing you can check is that to order V, if you multiply the G transformation with the inverse transformation, you get the identity. Okay, so here then we will have x mu minus A mu minus omega mu nu mu. So now let's do our favorite game of, okay, and then here I have to do some trivial Taylor expansion, right? Because these guys are small. So I just get phi b at x minus A mu d mu phi b of x minus omega mu nu x mu d mu phi b of x. Okay. So clearly, what I want to compute now is delta phi, which is evaluated at x, which is the value of the transformed field at x minus the original field at x. So it's essentially the left-hand side minus the leading term on the right-hand side, right? Because I have delta AB times phi b. And then everything else is to the right. So then I will get minus A mu d mu phi a from here. So I'm taking care of this, I'm taking care of this. Well, not completely care of this. Then minus omega mu nu. Let me try to write that in a way that. Okay, let me write it like this. Plus, sorry. Let me factor the parameter of the Lorentz transformation. And the first term I'm going to include is the orbital part of the transformation. That doesn't touch the index, right? Because I have this guy contracted with delta AB. And then I just get x nu d mu. And then I get plus I over 2 omega mu nu times this.
It's going to be minus I over 2.
No, change.
You have a minus in front of. Yeah, but here a plus, but you have a minus in front of.
Okay, good. Someone is checking me, that's good. Phi b. Okay. So that's the effect of translation. And this is the effect of a Lorentz transformation. Okay. So notice that that in the case of Lorentz transformations, I have the story I told you. So there is two contributions to the transformation. One kinematical, which is just the same for all fields, and one that knows about the specific field that you're talking about that acts on the internal integral. Okay. And this is true for an arbitrary field phi. I haven't told you whether it's a scalar, a spinor, or a tensor. The only thing that will change will be the choice of representation. Of the Lorentz field. So in the next lecture, what I'm going to do is do a similar analysis by slightly modifying this story, by letting the transformation be, in general, conformal transformation. And maybe something that if you have time and you want to think over the weekend, I already gave the answer away, but I said that in the case of conformal transformations, we have to specify not only the Lorentz properties of the field, but also the eigenvalue under the dilatation operator. So what I would like you to think about is why that's so. Why do I have to specify the value of the dilatation operator to fully determine how a field transforms under conformal transformation? And think about the story I told you before about how, if you know the transformations of the field at some point, how you determine the transformation of the field at any other point. And that should give you the answer. Since it's Friday, maybe I should stop early and let's continue one day. Well, it's not early, but not late.